Hello, everyone. Thanks for listening to our talk. In this talk, we're going to talk about our story of binary disassembly. But before I start our story, please allow me to introduce our team. We are a team from Stevens Institute of Technology, the Department of Computer Science. Our team includes Chen Bing, Eric, and myself. Chen Bing is a visiting scholar at Stevens, and he is also a PhD student at Nanjing University. Both Eric and I are faculty members at Stevens. Now it's the time for our story. Our story begins with the research project. In that project, we are expected to run formal verification over a group of lexicode. The lexicode mainly follows the format of x86 and x64 binaries. Our ultimate goal is to formally verify many temporal properties of the lexicode, for instance, whether the code terminates. But binary code is not a good format for verification because it involves too many low-level things. So the first thing we need to do is to produce some higher-level representations of the binary code. It is not hard to imagine that to get a higher-level representation from a binary code, the first thing we have to do is to disassemble the binary code. Specifically, our formal verification requires us to get the instructions, the functions, the pointers, and the control flows. The good news is we know that binary disassembly is a popular problem in the community for over 20 years. And on the market, there are dozens of disassembling tools available to the public. So to move quicker to our research goals, we planned to use an existing disassembling tool. At that moment, the key question to ask is which tool we should use. To answer the question of tool selection, we started looking at the performance of the tools on the market by referring to existing evaluation-based studies. It turns out that many tools can already achieve both high coverage and high accuracy. For instance, tools like Adapro and Anger can correctly recover over 95% of the instructions. We were happy about such findings, and then we started running several existing disassemblers to support our back-end verification tools. However, we could not achieve successful verification with the help of existing disassemblers. The reason is that, although the disassemblers provide statistically high accuracy, they still introduce errors to different types of results, regardless of the disassemblers we used and the programs we tested. More importantly, the errors frequently get propagated to the verification phase and hurt the results. Seeing the problems of using existing disassemblers, our first reaction is to understand why those disassemblers produce errors. Based on such understanding, we may be able to fix the errors. But how can we achieve such understanding? Well, our idea is straightforward. Let's try to understand the internal strategies used by those disassemblers and figure out which strategies make which errors. We started looking at the available sources of related information, such as documentations, papers, blogs, and forums discussing the strategies of the disassemblers we used. However, we quickly found that those sources of information cannot reliably help us build the understanding because those sources can be missing, incomplete, or inaccurate. Moreover, those sources can be outdated since they are not updated when the code is evolved. So in short, we need a better way to understand the existing disassemblers. So what else can we do to avoid the problems of information sources like documentations? Our answer is, let's look at the disassembler's source code which should represent the exact up-to-date semantics of the strategies being used. Following this idea, we picked a group of 9 open-source popular disassemblers, such as Ghidorah and Anger. We read through the source code to summarize the strategies of recovering instructions, functions, pointers, and control flows. To avoid errors during the understanding, we have at least 2 people looking at the same piece of code. After spending months on reading and understanding the source code, at the end of 2019, we were finally able to see all the strategies with first-hand details. In total, we discovered 44 strategies from the 9 disassemblers. The strategies can be roughly classified into 2 groups. 15 of the strategies are principled algorithms, which ensure the correctness of results. The remaining 29 of the strategies are heuristics, which rely on common patterns or inferences to do disassembling. We have demystified all the 44 strategies on an archive paper. If you want to see more details, please refer to our paper. As I said, 29 of the strategies are heuristics. Such heuristics provide no guarantees of the correctness, and not surprisingly, the use of those strategies are the root causes of errors. Here, we listed several examples of the error-prone heuristics. For instance, tools like Anger with neatly scanned code gaps left over by recursive disassembly. It can easily introduce errors when encountering data in code. For another example, tools like Ghidorah would consider integers that point to legitimate locations as pointers, which by intuition could make a lot of mistakes. Yes, now we know what are the strategies that will introduce errors, but we still don't know which strategies make which errors. To figure out which strategies make which errors, we decided to run an evaluation. We hoped to follow the setup of previous evaluation-based studies. In particular, we wanted to reuse the benchmark and their approach of producing the ground truth. However, we eventually decided not to do so. First, the benchmark used by the previous studies mostly consists of small size and functionally similar binaries. Such binaries cannot really represent the complexities and diversities of the real world. To deal with this problem, we built a new benchmark from scratch. We collected a group of differently sized and functionally diversified real-world programs, and we compiled those programs with different compilers under different optimization levels. At the end, we produced about 4,000 binaries. To the best of our knowledge, until now, our benchmark is the most comprehensive benchmark for the evaluation of binary disassembly. Second, existing approaches of getting ground truth of binary disassembly most rely on symbol information or debugging information. We found that such approaches can be easily inaccurate or incomplete. To deal with this problem, we decided to instrument the compilers. By tracing the compiling process step by step, we are able to get the accurate and complete information of different types of ground truth. Finally, also different from existing evaluation that measures a disassembler as a whole, we take a more thorough approach. We separately tested each strategy. Specifically, for each strategy, we wanted to measure how much contribution it brings, what level of accuracy it can achieve, and most importantly, we wanted to understand what errors the strategy will introduce. Throughout our evaluation, we testified our understandings of the source code and obtained answers to our remaining questions. First, we verified that the heuristics are indeed heavily used when the disassemblers handle real-world binaries. For instance, nearly half of the instructions are recovered with heuristics, and about 20% of the functions are detected by heuristics. Second, we empirically proved that the heuristics are not safe. All the heuristics make mistakes and introduce errors. Most importantly, we figured out which heuristics make what errors. Again, we have summarized the in-depth details in our archive paper. Following our findings, we then attempted to fix the errors by adjusting the heuristics to avoid those errors. The results were a surprise. While the adjustment of the heuristics avoided those errors, they tremendously reduced the coverage. For instance, when we disable the linear scan in anger, we can avoid the errors due to data encode, but we also eliminated the instructions and code gaps after recursive disassembly. So to sum up, the heuristics are actually trade-offs between accuracy and coverage. We cannot easily fix them to avoid errors without losing coverage. In other words, reusing the existing disassemblers may not be a good idea to support our research. Okay, so far, we have presented a successful understanding and a successful evaluation of existing disassemblers. But you may have noticed, our understanding and our evaluation actually rejected our idea of reusing existing disassemblers to support our research, because those disassemblers cannot avoid errors. But does that mean we killed the possibility of our verification-driven research? Our quick answer is no. From our study of the existing disassemblers, we gained many insights. One of the most important insights is related to System V x64 binaries, which are also the major targeted binaries of our research. Specifically, we found that the System V x64 ABI mandates call frame information for each function. Such call frame information is necessary to support runtime exception handling. Due to time limit, I will skip the details, but I want to point out two key things. First, the call frame information explicitly gives the start address of the corresponding function. Second, as I mentioned, the call frame information is needed for exception handling. As such, it cannot be disabled or stripped. This has been verified by our study of a group of commercial binary software. Yeah, now we know that the call frames give information about functions, but how can we use that to achieve correct binary disassembly? In our work, we developed a new approach to exploit the call frames to do binary disassembly. To be specific, we first extract all the function starts from the call frames. Then following each function start, we run recursive disassembly to detect instructions, function boundaries, and control flows. To ensure the correctness, during the recursive disassembly, we avoid using any heuristics. So based on my description, with call frames, disassembling is fairly straightforward, pretty much like drinking a smoothie. But is that true? Probably not. I mean, the reality is always more complicated. We found that even with call frames, we will still have to overcome many challenges for the sake of correctness. Here, I will explain two of the major problems and explain how we handle them. The first problem is related to non-continuous functions. To be specific, for the goals of optimization, compilers can often split their function to non-continuous parts in a binary file. For each part, the compiler will insert a separate call frame. As such, if we simply trust the call frames, we'll consider different parts from the same non-continuous function as different functions. Apparently, this is a mistake. Our solution to handle this problem is based on the observation that different parts of a non-continuous function are usually connected via a jump. Accordingly, we check if the jump has the same properties of the jumps between different functions. Or more formally, we check if the jump has the same properties of tail calls. If the jump is not a tail call, we can confirm that the destination part of the jump is not a new function. and therefore the source part and the destination part of the jump should be merged into the same function. Regarding how to determine a jump is not telco, we follow a set of novel but principled rules. For instance, if we see the target of the jump does not satisfy calling conventions, we can be sure that the target is not a new function and the jump is not a tailcall. Our second problem is related to jump tables. Again, for optimization goals, the compiler often compiles a switch statement into an indirect jump. The targets of the indirect jump are stored in a jump table, which correspond to the legitimate cases of the switch statement. Resolving jump tables to figure out the correct targets has been a major challenge in binary disassembly. To handle jump tables in our approach, we follow the idea of anchor. We use the technique called value set analysis to resolve jump tables, which gives theoretical guarantees of the correctness. We want to note that, although we follow the idea of anchor, we adopted an implementation that is customized for jump tables, which gives better results than anchor. By combining the reliable information from the core frames and our solutions to the previously discussed challenges, in the tasks of recovering instructions, detecting functions, and reconstructing control flows, our approach produces disassembly results that are more verification friendly. First, our approach achieves not only nearly full coverage, but also extremely high accuracy. Consider the detection of functions as an example. Our approach provides the same level of coverage as symbols, and provides the same level of accuracy as the best commercial tool, ABI Pro. Second, and more importantly, most of the missing cases or errors produced by our approach are harmless to verification. Consider function detection as an example again. The effects of any function we missed is equivalent to inline that function to its parent function, which has zero side effects to formal verification. Although we have some pretty good, or I would say satisfying results, our story is not ended. In fact, we're still facing and will be facing many key challenges in the face of binary disassembly. First, core frames can only give reliable information to recover instructions, functions, and control flows. However, they cannot help with the recovery of pointers, which are also essential for our goal of formal verification. To this end, we will need new approaches to reliably and correctly find pointers from binary code. Second, like I mentioned before, only System V x64 binaries mandate the existence of core frames. Other types of binaries, like Windows x64 binaries, have no such properties. So how to handle those types of binaries remains a challenge. Finally, the tools we're running still involves many engineering issues. We will have to investigate and fix those issues. Some concluding remarks. First, in our work, we fully demystify the strategies used by existing disassemblers. We believe this is the first work of this kind. The findings from our work will deepen the understanding about binary disassembling in the community at large. The findings will also help users gain awareness of the risks of using existing disassemblers. Second, we conducted the most comprehensive evaluation of existing disassemblers. We unveiled the performance and the pitfalls of each strategy of each tool. The results will bring new insights for the community to further improve binary disassembly. The results can also help users like us to select the tools that can best satisfy their demands. Finally, we exploit core frames to achieve verification-friendly binary disassembly. By doing so, we provide a new disassembling approach for users that have high requirements of correctness. Moreover, it brings insight of leveraging extra sources of information to facilitate binary disassembly. Now, we are happy to announce the release of the code and data from our work. First, like I have pointed out, the findings of our source code understanding and the results of our empirical evaluation are released in an archive paper. Second, we have released the data and code of our empirical evaluation on GitHub, including the benchmark binaries and our compilers to produce the ground truth. All of them are free to access now. Finally, we're preparing to release our core-frame assisted disassembler. Currently, it is available on request. Thanks for listening again, and I'm happy to take some questions now.